All right, another growth model is logistical growth. Logistical growth says that the growth of a population can't grow exponentially forever. And that's due to the environment. So there is a carrying capacity, which we're going to use capital K for. That is the maximum population the environment is capable of sustaining in the long run. And so what changes now in our differential equation is we still have that direct proportion to population, but we also got this 1 minus the population over the carrying capacity, which is going to be that limiting factor of the environment. All right, so let's first look at what these look like when you graph them out. Here is a directional field shown here that we've seen in the past for the logistical growth model, where K, little k, that's our growth rate, is 0.08 or 8%. And the carrying capacity, capital K, is 1,000. So that's what's shown here. Here's our 1,000, and you can see in our directional field that that is a that's going to be a solution there that is straight across, meaning if we start at 1,000, we stay at 1,000. It's an equilibrium solution. What they want us to do is draw solutions for these other populations. So what if we started at 100? So if we start at 100 down here, following the directional field, we're growing exponentially here, but now somewhere around here, it looks like we start leveling out and our directional field is not growing as fast anymore, and we would end up going towards that 1,000 carrying capacity. Same thing if we started at 400 as our initial population, we're growing, but it's slowing down as we reach the carrying capacity. If you'd start over the carrying capacity at something like 1,300 up here, now we're going to have our population drop off to that again, carrying capacity there. So what we're seeing here is that no matter what the initial population is, if you do the limit as the time keeps increasing out to infinity of our population, which is a function of time here, no matter where you start, it's going to approach that carrying capacity of 1,000. So logistical ones is always going, in the long run, is always going to advance towards that carrying capacity. All right, let's see if we can now, like we did with the exponential growth, take this differential equation and solve it out. So first thing we're going to need to do here is a little distributing. I'm going to distribute that P to both. I'm going to leave the K outside because that's not a variable like P is. So I'm going to leave K out here, but I am going to distribute the P to both. So if we do that, P times 1 is P, and then P times P is P squared over our carrying capacity there. All right, now let's separate it. So let's divide and get our stuff with P to the left. Let's move our dt over to the right, and now it looks like this. And our other side would be 1 over capital P minus P squared over K. And this side's going to be dP. Now let's integrate. Okay, the right side should be fairly easy, and we'll do that later. The left side there, that's our kind of our beast. That's the side that's going to be a little bit harder. So first, let's try to make this a little easier. Let's get a common denominator there. So I'm going to multiply that P here by capital K over capital K. And now I got 1 over KP minus P squared all over capital K. And let's make that a little bit nicer. We don't need fraction over fraction here. So let's multiply by K over K, which would make this equation K over KP minus P squared dP. All right, how do we now solve that one? Well, I gave a little hint up top here. What we're going to need to do to solve that is use some partial fractions. So let's factor out and see what would that be if we factored out this integral. It would be capital K over, looks like we can factor out a p there, so it'd be capital K minus p dp. So over on the side here, let's see if we can do some partial fractions there. So we have some variable like a over p as one of our parts of our common denominator. Let's use b over capital K minus p, and that should equal what our original one there, which is capital K over p k minus p. All right, so by multiplying by our opposite ones here, we would end up with a times k minus p plus b times p should equal capital K then. All right, this one a little bit different because we're not used to maybe having so many variables there, but we can still pick values for p here that would make it easier. One value of p that would make this one pretty easy to solve would be if p is 0. So let's solve that one. If p would be 0, then what we're going to have in the first one is just a times k. The second one's going to eliminate if p is 0 because it's just 0 times b, which is 0, equals capital K. And so if we divide by k, it looks like a is going to be 1. There's another value here that should make this one easy. If the population is the carrying capacity, then this one should simplify pretty nice. So in our first one, k minus k would be 0, so that whole first term is 0. Now we got b, we're putting k in for p, so bk equals k. Dividing by k again, looks like b is also 1 in this one. So now we can rewrite our integral over here in order to make this solving easier. So by putting in our values here, we should get 2 parts to this. So our a was 1, so this is going to end up being 1 over p. And our b was also 1, so 1 over capital K minus p dp. All right, now let's integrate both sides here. So if we integrate the left side, this is going to become natural log of our population. The next one's also going to be a natural log of our carrying capacity minus our population. Be careful on this antiderivative. Remember, our variable here is p, but it's negative. And so if you, by chain rule here, this would have to be -2, so that if we found this derivative using chain rule, we're going to get that extra negative by taking the derivative of the inside. So we should have a negative there. And the other side, our variable is dt, so this would just be little kt plus some constant. All right, so now we want to solve this. First, let's use our log rules on the left side. If we have 2 natural logs, same base number, and the logs are being subtracted, we know that changes into division of the first thing minus the second thing here. So we'll use some log rules first. All right, now let's change this from log form to exponential form. And so if we do that, this is what we're taking the log of on this side. On the other side then, we'd have e to the kt plus our constant. Let's do like we did in the exponential one now and separate that out on the right side here. So I'm going to write it as e to the kt times e to the c. And since e to the c is just both our constants here, I can write that as just some other constant. I'll use capital C here, e to the little kt. All right, so now we're getting closer to solving this one. Our goal again is to solve for p. it would be better if I did not have this division going on where I got two things in the denominator. So what I'm going to do is I'm going to take the reciprocal of both sides. And that's allowable because that'd just be like doing some multiplying and then dividing by the other thing. So if I take reciprocal of the left side, I got capital K over P over P. If I take reciprocal of the other side, it'd be 1 over C e to the KT. All right, now what I'm going to do is on the right side, or I'm sorry, on the left side, I'm going to split that into two fractions. So I'm going to have capital K over P minus P, capital P over P. And one of those simplifies here. If I simplify P over P, that's just the same as minus 1. Okay, now I'm going to add that 1. Well, actually, first I'm going to do something with the right side here. We could, if we wanted, move this up to the numerator. And by doing that, that's going to switch the sign on that. So that would switch the sign, or not switch the sign, switch the sign of the exponent to negative. So this would be e to the negative kt. The c, we could also have like 1 over c, which is still a constant. So again, I'm just going to keep this as some other, it's still some unknown constant. I can still keep it as a c. Now I'm going to add that 1 to the other side. And I got c e to the negative kt plus 1. And then we want to solve for p. So I'm going to times by p and then divide by all this. So if I times by p and divide by all that, now I've solved for p. Or I could just think of it as taking the inverse or the reciprocal of both sides. So we end up getting that p would be equal to capital K over c e to the negative kt plus 1. And that right there ends up being the population function for logistical growth. Here's another view of it. They switch a little bit of the variables here, but same idea. We had our carrying capacity on top. That was same as what we just solved for. P is our population as a function of time. We had that plus 1, which was in our denominator. It was just on the other side. We got this e to the negative kt, where t is our time, k is our rate, or our population constant. E is our natural number. We can see our negative that we had in there. The only different variable in this one is that a. In our other one, we had c there. They're just using a different variable, but that was the constant we had from integration. And in this case, that a, that constant there, is going to be our carrying capacity minus our initial population, all divided by, again, our initial population. So that, when you're using logistical growth, this is the formulas that you want to know and use when solving any logistical growth problem. You can get it by solving the differential equation, but as you just saw, that was quite long. So I think these are equations you're probably going to want to know for the test, because you're not going to want to have to take the time to solve all that out.